So now we have Ben Evans, which is talking about HPC or CFD.
Yeah, how are you?
Hi.
Good. Morning, everyone. These guys from SA2C, by the way, they're really, really good. If you've not engaged with them at all, you should. And I don't know why I'm advertising this, because I feel like the more people that engage with them, the more demand there's going to be on your time, inevitably. And they've done some bits and bobs with some of the work that I've been doing. And over the course of the last 6 months, we've managed to get some of my code to do things that I could have only dreamed of achieving myself, or it would have taken several PhD projects probably to get to the point where they're doing what they're doing now. So I do really recommend engaging with them. Thank you very much to Mark and Co and Ed for inviting me to talk today. I started thinking about what would be a good thing to share at a forum like this. Mark told me, don't go into all the nitty-gritty about CFD because not everybody's going to be interested in CFD. So I thought to myself, it reminded me of a talk that Bob Laramie from Computer Science gave in one of our symposiums over in engineering a few years ago. And he got up and he said, right, I'm going to give a talk, and all I'm going to do is just show you lots of pictures and tell you some stories. And it's one of few talks that I've sat through that I still remember. So I thought, I'll give that a go. So what I'm going to do, if it's okay with you, even if it's not okay with you, because it's all I've prepared to do, is just show you some nice, pretty pictures, some videos, and I'm going to tell you some stories about how HPC allows me to do the work that I do, if that's okay with you. You'll notice I added in the word cool into the talk title. High-speed cars, boats, and other cool things. I found preparing for this almost like a therapy session because a lot of the work I do sometimes feels a little bit disparate, and I've tried to bring it all together into one PowerPoint presentation, which was quite a nice kind of therapeutic process for me. And then I looked back at all my slides and I thought, you know what, it's quite cool, some of the stuff I do. So I added the word cool into the title. So, and I promise I will have everything wrapped up before 11, so we're not late for coffee. This picture landed on my desk about a decade ago. I was wrapping up a PhD in computational fluid dynamics. The work I was doing back then was looking at molecular descriptions of gas flows, mathematically via an equation called the Boltzmann equation, and trying to figure out if we could solve this using finite element methods. Honestly, if back then you'd asked me what HPC is, I wouldn't have really been able to answer that question. Jason Jones is smiling because he'd probably say I still couldn't answer that question. Yeah, be careful. But over the last decade, it's become obvious to me that I simply cannot do what I do without high-performance computing. This picture landed on my desk. There's a note attached to it. I was planning on leaving the university and going to get a proper job. There's a note on it asking me to go and see my supervisor, who was Professor Ken Morgan. And it turned out that a chap called Richard Noble, who is an ex-land speed record holder, he was the project director on the Thrust land speed record program, which developed the Thrust SSC car, which holds the land speed record today. I got in touch and said, we're going to have another go at this. We're going to take a British land speed record car up to a target speed of 1,000 miles per hour. And for the last decade, this has been a joy, stroke the bane of my life to work on. And the design for this car has been driven almost entirely using computational fluid dynamics. So a land speed record vehicle, or whether or not a land speed record vehicle is successful, is almost entirely driven by the aerodynamic forces acting on the vehicle. There are some other things you have to consider. But to get to the external packaged shape of this vehicle, so an external geometry, which is what drives the aerodynamic response of the vehicle, you need to understand the aerodynamics. You need to understand how much lift or downforce will be acting on the car, how that varies as a function of the vehicle's speed or the vehicle Mach number, and how much drag will be acting on the car. So we went through a process which started all the way back in late 2007. First of all, trying to answer the question, is it even physically possible to take a vehicle of this sort of size along the surface of the Earth at 1,000 miles an hour? Can that be done? And then second of all, if it can be done, what shape should that vehicle look like? And that process was driven by CFD. Now, I'm going to try and avoid I'm not going to put any equations up. I'm going to put a few little bits and bobs of stats up because I guess HPC people are interested in this kind of thing. So the kind of simulations we're running here are RANS-based simulations, so based on solution of the Navier-Stokes equations in their Reynolds average form. So they're time averaged, which then requires you to use turbulence models to try and understand what's happening at the subgrid scale and at temporal scale smaller than your time steps. But to run a single steady-state CFD solution on a problem like this, on a grid size of the order 100 million cells, would typically take about 24 hours to get to a steady, converged solution across 256 cores of the HPC Wales machine, as it was back when we were running these types of simulations. So there is no way we could have done what we did on Bloodhound without HPC. And that's a single simulation of the car at a given Mach number, so a given set of kind of free stream aerodynamic conditions. But we want to know how this car responds all the way down to, say, Mach 0.2, Mach 0.3, where it's traveling at maybe 200, 300 miles an hour, right up to 1,000 miles an hour. So what we do is we run a series of snapshots at different speeds to build up a picture of how the car behaves across the speed regime it's going to be running at. And that information then feeds into the wider design cycle of the car. So this is config 0. This is the first set of the geometry on which we ran the first set of CFD simulations a decade ago on that initial artist's impression of what the car should look like. And it took us about 5 or 6 years to come round this loop and arrive at the car that we built, which is actually config 13. But Richard Noble has told me never to present a presentation where I tell him that the car we built was number 13, because some people get a bit funny about the number 13. So I always stop at config 12. So again, you can get an idea if at every point in this cycle, so every time we change the car geometry, we're running maybe 20 or so of those 256 core 24-hour simulations. Heck of a lot of HPC resources gone into getting us around this loop, and it's actually taken us it took us about 5 or 6 years to get to that final design. Once we kind of had nailed the external package of the car, we then started homing in on some other things that might have been of interest. So one of the questions I was asked was, how are the air brakes on the car going to affect the flow downstream and the part of the car that sits downstream of these air brakes? So just to give you an idea why we need the car to slow down, we're going to run this car on a 10-mile track. In the middle of the track, there's a mile where the average speed of the car will be measured, and we've got to get the car to be an average of 1,000 miles an hour over that mile to get a 1,000 mile per hour record. At 1,000 miles an hour, you're traveling a distance of a mile every 3.5 seconds. Okay, so imagine getting from here to somewhere a mile away. That will take you 3.5 seconds. Our track is 10 miles long, so at the end of this measured mile, where we're traveling at 1,000 miles an hour, we've got just under 5 miles to stop. Okay, so actually getting the car to stop is every bit as challenging aerodynamically as getting the car fast in the first place. So we need braking systems. The drag of the car alone is not enough to get it to decelerate in that distance. So we open out these big barn door air brakes on the side of the car. Now, in a design meeting a few years ago, someone asked me, do you have any idea what the flow field looks like downstream of those doors? Now, of course, once you open big kind of bluff bodies into flow like that, the flow you get behind them is really messy. There's a lot of vortex shedding and unsteadiness. And up until that point, everything we'd run was steady-state simulations. We weren't trying to track the time history of what was happening. But I said, well, we've got big computers. We can throw this at this. We can run this problem unsteady. So we're trying to actually capture the time history of the solution. And they were interested in knowing what the vortex shedding frequency at various speeds of the car would be on those air brake doors. So we ran a set of simulations focusing in on just the air brake behavior. Again, a similar sort of sized mesh, but this time running in real time. So rather than trying to converge to a steady state solution, trying to pick up the time history. And again, this is expensive, 256 cores. It took about 24 hours runtime to get about 1 second's worth of real time history at a sufficient resolution to capture this vortex shedding. And I went back to the meeting and I said, so the vortex shedding frequency of the air brakes as they first existed, like in this picture here, just a solid door, is about 1 to 2 hertz, typically. And we turned to the structural engineers who designed the rear wheel suspension and fairing system here, and we asked them, roughly what's the resonant frequency of that system? And they said, 1 to 2 hertz. So we said, oh, I think we used a word that I probably shouldn't say because this is being filmed. So we had to come up with a solution. And the solution eventually was simply to punch a load of holes in the air brakes. There was a small penalty that you paid in terms of how much drag they generated, but not as much as you might think, considering how much less surface area there is now. And what they ended up doing, actually, was instead of having very large, relatively low frequency vortices being shed from the air brakes, we ended up having lots of much smaller, but much higher frequency vortices being shed that we hope is far enough away from the natural frequency of the rear wheel system not to shake it apart. At the same time as all of this, I promised I'd tell some stories. So I was sat in a cafe down there, Callahan's. Is it still a thing, Callahan's? Yeah. This is why I love universities. I was sat there drinking my coffee. It wasn't the drinking the coffee is the reason I love working at universities. But someone came over to me from computer science and said, oh, over there's a guy I've been meaning for you to talk to for a long time. Have you got a few minutes? So I said, yeah, fine. And the guy's name was Matt Edmonds. Anybody know Matt Edmonds? He used to be a computer scientist, and then he saw the light and came over to engineering and worked with us. And he was doing a PhD on data visualization, and he'd been wanting for a long time to try out some of his techniques on CFD data sets. So he basically said, this is what I do, this is the data I would need, this is roughly the format I'd need it in, let's see what we can do. So I just sent him a download link to some of the data sets that we'd recently run on this particular problem. And within an hour or so, he was emailing me back pictures that looked like this, which I thought was really cool, because up until now, to generate flow visualization of my CFD data sets would be an incredibly manually intensive kind of piece of work using software like ParaView or Nsight or something like that. You play around for ages trying to seed your streamlines or stream surfaces to pick up the phenomena that you want. And he had this capability to just load in a data set, look for the interesting features in it, visualize it all automatically. We'll come back to that story later on. So we're not just interested in what the air is doing to the car, but we're also interested in what the air is doing to the ground that the car is rolling across. And thanks to Jason Jones, because he produced these visualizations for me. So what we've been doing as well is looking at the effect of, particularly when shock waves start being generated, as we go through the transonic regime, by about Mach 0.8, 0.85, we start generating shock waves, which are these big purple things here. Because what they found on the thrust project was one of the problems they had is you've got to run the car back in the opposite direction, and it's the average of your 2 runs in opposite directions that gives you your land speed record. But the shock waves they were generating were actually pulverizing the surface that the car was running across. So by the time the car was running back in the opposite direction, the surface had been almost destroyed. And we're going to be running 30% faster than thrust did. So we realized pretty early on this is going to be a big problem for us. So we specifically used design optimization techniques to get the underside of the car such. So on the left-hand side is quite an early configuration of the car. The right-hand side is the current design of the car. To try and minimize the impact of the pressure distribution generated by the aerodynamics on the ground plane. So you can see these are using the same pressure coefficient mappings. So you can see we did a pretty good job there of trying to minimize the impact of the pressure distribution over the ground plane. This stuff down here, don't need to worry too much about that because that's at a point where the grid has become too coarse to be accurately capturing what's going on. Anyway, to cut a long story short, we ended up designing this car here. We built it over a period of about 18 months, and the build was finished towards the end of last year. So we thought it would be fun last year to take this to a UK runway and see what we could do on a UK runway. So let me just show you this video. I'm hoping we're going to get some audio, but yeah, we do. So back in October 2017, we took the car to Newquay Airport, which has got one of the longest, it's a military airfield, or an ex-military airfield. And it's got one of the longest runways that is relatively underutilised in the UK, which is why we went down there.
Clear to roll, wind 2 o'clock, 5 knots.
I still can't decide whether watching this car rolling at 200 miles an hour gives me more confidence or makes me more nervous about trying to take it to 1,000 miles an hour. But we had a lot of fun that day. There was a lot of conversation on the day. So we took the car, I think that the peak speed we got the car up to was about 212 miles an hour. And there are a lot of people there going, yeah, hang on now. I mean, a Bugatti Veyron can go faster than that, and you could go out and buy one of those if you had enough money. And then someone said, yeah. I think it was Andy Green, in fact, in one of his interviews. He said, yeah, but a Bugatti Veyron takes, I think, 22 seconds to go from 0 to 200 miles an hour. On that run there, it took Bloodhound 6 seconds to go from 0 to 200 miles an hour. So it's a pretty impressive machine. And that's a car, we haven't even put the rocket system into it yet. That was just operating off the jet engine on the car. So, I promised I'd talk about some other things. So, in parallel with all of this going on, obviously a lot of my time gets taken up working on this project, but I became very aware that there's a risk career-wise for me that at the end of Bloodhound, I become the world expert in designing land speed record cars. And for the rest of my career, there is no demand anywhere in the world for a designer of a land speed record car. So I thought it'd be a good idea to diversify my skill set somewhat. And I was having a conversation with Richard Noble at a Bloodhound meeting once, and he dabbles in lots of different things, and he has some interests in the marine industry. And he said, one of the things you might want to start thinking about is what impact some of your CFD methods could have on the marine industry. Because CFD now in the aerospace sector is a pretty mature, established tool. So if you go to Airbus, Boeing, Fokker, Embraer, they'll all be using CFD as standard practice in the design process to design aircraft or features for their aircraft. The marine industry is probably a generation behind where the aerospace industry is in terms of implementing computational tools. They still design even extraordinarily expensive, marine, like ocean-going liners using kind of rules of thumb and kind of engineers doing a bit of this and sticking something they've tried in a flow tank. There are people dabbling with CFD methods for kind of hydrodynamic design, but it's nowhere near at the level of maturity that it is in aerospace. So we thought, well, this would be an interesting thing to have a go at. And we partnered up with a French naval design company who are based in Cannes in the south of France, which is quite nice when we get to go and visit them. And we started looking at what kind of problems are they trying to solve. Could we solve these using computational tools and high-performance computing? And they sponsored Jack, who is just rounding up his final year of a doctorate project. So we started running simulations like this using a lattice Boltzmann technique. So we started thinking about, well, could we adapt the kind of Reynolds average Navier-Stokes type CFD that we use for Bloodhound and aerodynamic analysis for this? But really, one of the big problems with hydrodynamics for marine craft is the problem of, if I can play that again, or maybe I'll show you on the next one, is the problem of how do you track the free surface? So that's a really challenging problem, is first of all, how do you track where it is, and then how do you deal with it in a RANS environment, even if you can track it, particularly when it becomes extremely high fidelity and complex and evolving. So we decided to move over to a technique known as a lattice Boltzmann technique, where essentially instead of solving for the traditional fluid properties like pressures and densities and bulk velocities, the thing you're solving for is a probability function, the probability of finding a molecule or a particle at a particular point in space with a given velocity. And the lattice Boltzmann method then restricts the possible velocities these particles can be traveling at to align with the grid that you're using. That's basically the idea behind it. And we found that, yes, we can solve these types of problems. We did some experimentation over in engineering where we stuck an equivalent model wired up with pressure tappings across the hull to see if we could get the same kind of response that we saw in the flow tank in the CFD model. I think I can play that again for some reason. But very quickly, we realized this is expensive. So in this case here, to replicate this real-world flow tank example on a grid which is still relatively coarse, so 3 centimeter grid size cells. To keep this scheme stable, we ended up needing a time step of about 30, what's 10 to the minus 6? Microsecond, isn't it? A microsecond is 10 to the minus 6. So to simulate a reasonable amount of time, in this case we simulated 10 seconds, required almost 300,000 time steps, which on a grid here, which ended up being about 100 million cells, took 72 hours of runtime partitioned across 600 cores of the HPC Wales system. So this is really expensive, and still one of the challenges of implementing hydrodynamic modeling into the marine design cycle is running these types of models is really, really expensive. And if you're interested in capturing features like a high fidelity wake, so one of the things the company were interested in, they particularly specialize in high speed marine craft, is how can we minimize the effect of the wake, or what effect does the wake have on craft that are traveling behind it. The kind of resolution you need makes the simulations really, really expensive. So here the grid size reduced down to a centimetre on a boat this boat, how long is this boat, Jack? About 15 metres long? 15 feet long. So we ended up with a grid size of about 250 million cells. And again, we're running there on 500 cores for 120 hours to give us just a few seconds snapshot of the response of this vessel. One of the things they were particularly interested in, because up until now they've just used back of the envelope calculations embedded in a big fancy spreadsheet to figure out, for a given boat hull that they're designing, what position the boat would sit at for a given flow speed. So one of the problems they gave us early on was, could we predict, I'll show you, could we predict where the boat would sit in the water if they gave us a hull form and then they told us the flow speed they wanted to run the boat at? Could we predict where the boat would sit in the water? So that was our kind of first test of, can we get this right and do something useful for them? And we got these pretty much spot on for them, didn't we? When we sent our results back saying this is where we think the boat would sit in the water at this particular flow condition, it pretty much directly mapped to what they were predicting through their empirical methods. At the same time as all of this was going on, we're okay, we've got 10 minutes left. In parallel with all of this, the lovely people at HPC Wales, as it was back then, and Fujitsu, decided that they were interested in sponsoring some research of mine. So they sponsored a PhD student. We decided we would look at a project in the area of computational optimization methods. So one of the frustrations that I'd had working on Bloodhound was the bottleneck in the design cycle that happens when you're going from a CAD-based geometry, so a vehicle geometry in a CAD system exported as an IGES file or a step file, through to the CFD mesh. That was always the bit of that design loop that caused us headaches and a lot of kind of manual intensive work. So we decided we'd try and develop a scheme where instead of, once you've generated your initial mesh, instead of going back to the CAD system every time to update the geometry, you would just mold the mesh. So you would actually use the mesh itself as the parameterization method for the design optimization. So I'm going to run this. I'm going to just stop it here. So we did some work with a PhD student who I was really hoping would stay here and do a postdoc, and then he realized that Airbus would pay him a lot more money, so he's gone to work for Airbus. And we started solving these types of problems, partly because they're difficult. So this is a design of a transonic aerofoil. So this is 2D. And what we're trying to do here is, starting with a fairly generic airfoil shape, so what's called a NACA 0012, which is a symmetric aerofoil. We are trying to get the optimizer to design an aerofoil that we already know exists by giving it the known pressure distribution over that aerofoil. So it's trying to change the geometry of the aerofoil in the direction of a known solution. But to do this in the transonic aerodynamic regime is really difficult because of how sensitive transonic aerodynamics is in terms of positions of standing shock waves and instability of CFD solutions as well in this regime. So this is what happened as the optimizer was evolving. And this is a case where we were running what's known as evolutionary optimization. So rather than have a single solution at each iteration that gets modified, we run a family of designs. In this case, 100 what we call nests in the language of the particular optimizer we're using. So there are 100 designs being tested at every iteration. They're being ordered into the best designs and the worst designs. Interbred is the language often used to spawn new designs in the next generation. It took about 700 generations for the optimizer to get pretty close to the target geometry. So this is, I mean, it sounds like a fairly simple problem. So it's a 2D optimization case, 11 degrees of freedom. The individual CFD solutions here will only take a few minutes to run on a single core. But because we're using evolutionary optimization with lots of agents and many generations, this actually ended up taking 12 hours to run on 100 cores of an HPC system. So to bring these threads back together, I'm going to show you this. So a couple of years into the project with Jack, the company down in France, who we'd been working with doing hydrodynamic modeling, came to us and they said, one of the things we'd really like to do is get into XCAT racing. Has anybody come across XCAT racing? It's flipping nuts. Like, yeah, it's proper nuts. So this is like the Formula One of powerboat racing, okay? You've got to be a little bit crazy to get in one of these boats, I think. So they are, and this is, for whoever's editing the video, this next slide is the sensitive bit that we're not allowed to go out, okay? And you're not allowed to tweet this stuff, because nobody knows they're working on this. So they said to us, well, could you help us design an XCAT boat that we want to enter into the next series of XCAT races, which will happen next year? And we said, yeah, fine, what's the problem? And they said, basically, this is all about drag reduction. Like everything in XCAT racing is about how do you minimize the drag. So we started looking at this from a hydrodynamic point of view, like what you can do to the hulls to try and minimize the hydrodynamic drag, but it pretty quickly became clear that basically the solution to drag minimization on an XCAT boat, yeah, it's a bit scary, isn't it? is basically how high can you get the boat to ride in the water? Like the more the boat you can get out of the water, the lower the drag. And we quickly realized that then became an aerodynamic problem, as you can probably see from these. I mean, these are almost low-flying aircraft rather than boats. So they asked us to design the aerodynamics of the tunnel that the air flows through between the two sponsons on the catamaran in order to maximize lift. They didn't, and this is an interesting optimization problem from an aerodynamicist, because usually what you're trying to do as an aerodynamicist is maximize lift whilst minimizing aerodynamic drag. But in this problem, they said, we don't care about aerodynamic drag. Aerodynamic drag is going to be so small compared to the hydrodynamic drag. Any additional lift you can generate by molding the tunnel design of the catamaran is going to lift the boat out of the water, and the drag reduction by reducing the hydrodynamic drag will kind of swamp any additional aerodynamic drag penalty. So we thought, so at that time, it was quite convenient. David was coming to the end of his PhD in aerodynamic optimization. He said, well, actually, we've got a tool for doing aerodynamic optimization. Now, it turns out, the reason I laughed earlier is because I think Mark was directly referring to me when he said, you'll find you have a PhD student who writes some code and then it sits somewhere for a couple of years and you go and run it and somehow some bugs have crept into it. We found exactly that was the case here because we hadn't controlled the code development in any meaningful way. But eventually we managed to get it running. And this is the bit you're not allowed to show. We started off with this baseline geometry. This is a slice down the center line of the tunnel of the catamaran. And this is how, so we're running 20 nests, that's 20 designs per generation, and interbreeding them to try and find a maximum lift value that we could get. This is the mesh evolving as the optimizer is evolving. And we managed, in the space of 24 hours, running on just 60 cores of a machine, so to get a lift enhancement of about 25% on the boat. So we went back to them, and in reality, it took us weeks and weeks and weeks to get the code working. But actually, running the code to solve the problem they wanted took us a day. And then we managed to give them a design that they're now implementing into a 3D model for their XCAT boat with a center line that looks like that, which, as an aerodynamicist, is not obvious why that is a better design, a higher lift design. I think we do understand it now. But anyway, so that's work that's been going on. And I'm going to wrap up fairly soon. So just to give you an idea of some of the other cool things that we've been throwing these ideas at. A year or so ago, does anybody know this? Does anybody recognize this car? I'd never heard of it until they approached me. So this is a Bond bug from the 1970s. It's like a cult classic. It was a sister project to the Robin Reliant, which you probably will have heard of. Anyway, there's a company who approached me who restore classic cars and re-release them in kind of 21st century editions. And they said what they really wanted to do is take the Bond bug design, they'd acquired the rights to it, and release, and they're going to do this in 2 years' time, an electric version of the bond bug, okay? And I think it's quite cool, and I'd really quite like to get one. But they said to make this work, what we would need to do is reduce the aerodynamic drag on the car by 30%. Do you think you could do that? And I looked at that and I said, well, it kind of looks like a brick. So I'm fairly confident we could knock quite a lot off the drag. And so we threw our optimization and CFD techniques at that and have ended up with this outer package here. And that's actually being made now. So that's going to be released as an electric bond bug out in 2020, I think. We've been working with people like Fokker GKN, the aircraft manufacturers, looking at winglet design and novel ways of minimizing wingtip vortex drag. Some work that Jack did using optimization methods based on design of experiments approaches to design the rear wheel fairing for supersonic drag reduction of the fairing for Bloodhound. We're working with a company at the moment who are going to produce a hybrid electric light commuter aircraft. We've been helping them design the end plate for their kind of triplane design. Can't show you the final designs because they won't let me. And some work that I've worked really closely with SA2C on, which has been amazing. So this was the kind of PhD stuff I was doing, looking at molecular gas dynamics. This is a 2 nanometer diameter particle trapped inside an 8 nanometer diameter channel. And it turns out that it's still a really difficult thing to do to predict the drag acting on that in, as a function of Reynolds number or Knudsen number of the flow, the kind of degree of rarefaction of the flow. So we had a go at doing this, but it was just really, really expensive because the way it's based on a solution of the Boltzmann equation, which is inherently expensive. And I'd had ideas about how to better parallelize this for years, but just never managed to get the funding or the right PhD students in to help me work on that. Mark came along and said, well, we've got RSEs now who help people like you do exactly that. We know that you've got a problem, that the code isn't parallelized particularly well. And Michele came along and worked for a bit of time on this. And we've now got a version of this code now that used to scale up to about 16 cores, and now it will scale up to many hundreds of cores, which basically opens up a whole new array of things I can do. To give you an idea of where all of this stuff is going in the future, one of the things that's dawned on me working with engineers in industry in aerodynamic optimization and hydrodynamic design is there seems to be two schools of thought going on. There's one camp that put all their eggs in computational optimization methods. They basically give their problem to a computer and say, tell me what the design should look like. And then there's another school of engineers who say, show me the CFD results. We'll sit down around a table and a PowerPoint presentation and discuss the implication of those results. Then we'll sit down at a CAD desk and sit with someone and change the design and we'll try it all again. So I've got a project that's in its tentative stages at the moment where we're trying to merge those two ideas. So bring the human into the computational optimization loop. So as a computational optimizer is running, and you can see they're expensive, these things can run for days and days and days. But what if a human designer could drip feed his thoughts and influences into that process in real time? And one of the tools that will allow us to unlock this, I think, is some of the automatic data visualization stuff that computer scientists over here can do. So these are some ideas that I've been working on and I'm going to continue to work on over the next few years. So I promised that I would just show you pictures, but just to prove that I do also do some proper work, on my final thank you slide, I'm just going to prove to you that we did publish some of this stuff as well and do the proper job of an academic. So thank you very much for listening. Diolch am wrando. I think we got a few minutes if anybody has any questions. Yeah.
Thanks,
That's right.
So I was wondering, coming from working currently on more structural mechanics and thermal mechanics, those kind of things, whenever you put things to optimize it, quite often you end up with kind of biomimicry because which is a good way of evolving to be optimized structure. Why within fluids are you not getting? Are your constraints so much that you're not getting to that point, or is it something that's different?
Yeah, I think it's a really interesting question and something that I'd love to explore. I think largely the answer to the question is the constraints that the industry places on what you're allowed to do force you down a particular route. Like an aeroplane looks the way it does, not necessarily because it's the best aerodynamic shape. It's because that's how we built airplanes. I mean, there are good reasons for that. Pressurizing a long tube is easier than pressurizing something that looks more like a bird. But one of the things I'd love to throw these tools at in the future is, constraint-free optimization. You don't give it any hint at what this thing should look like. You say, optimize the lift to drag ratio of this body, I'll give you a sphere, no constraint, and see what you get. And you'd like to think you get something that looks a bit like a bird. But yeah, everything I've done, I think because so much of what I do is so industry focused, if I said to them, here's the plane that I want you to go and build, it looks like a bird, they would just laugh. But yeah, it's a good point.
So what happened? So the Bloodhound set the speed record, I guess.
No, not yet. I wish it had. I wish I could say all of that was in the past. We're still plugging away. We were hoping to take the car to South Africa this year, which is where we're going to do the high-speed testing. But we're in various negotiations with some of the sponsors of the project who all have competing demands on what they want to try and get out of it. So it looks like it's going to be spring next year that we take the car to South Africa. So we've taken the car to 210 miles an hour. Really, to be honest with you, that was really a PR exercise more than anything else. We learned a little bit about the car behavior, but nothing, certainly from an aerodynamics point of view, nothing particularly meaningful. To go any faster than about 200 miles an hour, we need more track than a runway offers us. So we'll be running on a desert in South Africa. My anticipation is within a couple of years. I think next year will be a testing year where we learn lots about the car. The year after, we'll go back and have a bash at breaking the current record. If I'm honest, need to be careful what I say because this is going out. I'm still in two minds about whether 1,000 miles an hour is actually possible. I mean, you know, 763 miles an hour. But there's a big gap in our understanding of how a vehicle like this behaves between 763 and 1,000 miles an hour. You know, I think it's perfectly feasible that we get to 850, 900 miles an hour and just find there's something fundamental that we haven't considered yet that stops you going any faster. If you're a potential sponsor of Bloodhound, ignore what I just said, by the way.
What FE framework do you use? Do you draw your own? Or
Sorry?
what FE framework do you use?
Yeah, it's all in-house stuff that we've written. The lattice Boltzmann stuff for the Aerodynamics is an open source solver called Palabos, but all of the FE stuff for CFD is all in-house stuff that we've written over in engineering. Yeah. But it is going to be open sourced, all of that, Jason assures me. So Jason here is going through the process of open sourcing. This is correct, isn't it? Open sourcing all of the in-house codes that we've used to do all of the work in here.
Apart from the old academic that's made a serious amount of money out of it, they go open source their stuff.
Yeah. So that's an ongoing process. Is there a hand up down here?
Well, I have At what point are you disqualified from the CATX races for having a low-flying airplane?
Yeah, that's a good question. Yeah, do you know what? I don't know the answer to that. I mean, the land speed record is really simple. You've got your wheels are going to be touching the ground. I don't know if there's a similar rule in XCAT. But you're right. I mean, lots of the boats that are doing the best are basically the ones that are just skimming the surface and generating just enough lift to lift them just off the surface, which is what we're trying to do. Yeah, I don't know the answer, to be honest.
So the aerodynamic optimization stuff.
Yeah.
And it's 2D, it's quite simple.
Yeah.
So is that going to be prohibitively expensive then going to 3D?
It's going to be expensive. Yeah, it is going to be expensive. I mean, you look at the cost of running a 2D optimization on an aerofoil, where you've got 11 degrees of freedom, you're running whatever it was, 100 nests, you're talking 24 hours on 100 cores, where we're running each CFD simulation on a single core. Once you're in 3D, really you need to be partitioning the CFD simulations as well as running multiple design, and the number of degrees of freedom you need to parameterize the problem goes up. So you might be wanting to run 500 agents where each agent is a CFD solution partitioned across 256 cores. So, but it's all, everything, in principle, the ideas scale, you just need more, you need a bigger hammer to hit your nail with.
Yeah. But presumably each simulation then is completely independent.
Yeah, totally, yeah. I mean, one of the things I think we've talked about this in the past is the idea of, farming out CFD solutions to different systems. They don't have to, the nice thing about evolutionary optimization is at each generation, all the designs you're testing are completely independent from each other. There's no communication between them. So you could farm off CFD solutions to, clusters all over the place, get them back each generation, analyze your data, throw them all out again. There's all sorts of ways of getting around, that.
Any more questions? If not,
Thank you, Michele. Thank you, everyone.